Hello everyone. In this lecture, we are discussing molecular electronic spectroscopy, wherein we are considering the electronic transitions in a molecule. We have talked about the Born-Oppenheimer approximation in previous modules, and this approximation can be used as the first approach to the electronic spectra of molecules. By the Born-Oppenheimer approximation, the total energy of a molecule in the ground state is given by rotational energy plus vibrational energy plus the electronic energy. The total energy change for an electronic transition also can be expressed as delta E total, as delta E electronic plus change in the vibrational energy transition plus change in the rotational energy transition. As we seen in the introductory lecture, the electronic transition will have higher energy than vibrational, which have much more energy than the rotational transition. So, the electronic transition possess the vibrational and rotational fine structures. The electronic spectra are generally very complex as it involves vibrational and rotational transitions. It is observed in the UV and visible region of the electromagnetic spectrum, that is a higher energy region than the rotational or vibrational spectroscopy. We should also know that whereas pure rotational spectra are shown by only molecules possessing a permanent dipole moment, and pure vibrational spectra are shown by molecules where there is a change in the dipole moment during motion, the electronic spectra are given by all molecules, since it needs only changes in the electron distribution of a molecule. So, for homonuclear diatomic molecules, which shows no rotational or vibrational spectra, do give electronic spectra and show vibrational and rotational structures in their spectra. From these vibrational and rotational structures, we can find the bond frequencies and rotational constants. Here we will focus only the vibrational core structure of electronic spectra, since if we are including the rotational levels along with this, it will become more complicated. So just we are dealing the vibrational core structure only, that is the electronic level containing vibrational levels. Here is a picture which shows the energy levels of two different electronic states E0 and E1 of a diatomic molecule, having the vibrational levels V double prime in the ground state and V prime in the excited electronic state. This is, the Morse curve for an harmonic oscillator. Since an enharmonic oscillator has selection rule as delta V plus or minus 1 plus or minus 2, etc., we may expect a lot of transitions here. So we can simplify the situation by thinking that the absorption starts from the ground electronic state only, so that we can have the transition V equals to V double prime 0 to V single prime 0, V double prime 0 to V single prime 1, V double prime 0 to V single prime 2, then V double prime 0 to V single prime 3, etc. Thus, the electron spectrum would contain the different lines and this vibronic transition, that is vibrational transition between two electronic levels, so-called vibronic transitions, are represented as V prime, V double prime, in brackets V prime, V double prime. So 0, 0, here the 1, 0 transition. What would be this? The 2, 0 transition, 3, 0, 4, 0, etc. As there is a set of transitions, it is always called a band. Look into the intensity of the vibronic spectrum. In some spectra, we find 0, line to be more intense, and in some other spectrum, we will find 2, will be strongest, or it can be any other line in some other cases. A very useful guiding principle for investigating the vibrational structure of electronic spectra is provided by the well-known Frank-Condon principle. It states that an electronic transition takes place so rapidly that a vibrating molecule does not change its internuclear distance appreciably during the transition. This principle to a first approximation true, since the electrons move so much faster than the nuclei that during the electronic transition, the nuclei do not change their position. Let us demonstrate the Frank-Condon principle for the electronic transition of a diatomic molecule. Consider this figure where we have shown two potential energy curves for the molecule in the ground electronic state and the excited electronic state. The difference in the equilibrium internuclear distance is R equilibrium for the excited state and the ground state can actually give rise to different mode of transition. So let us look into some different possibilities of this transition. First one is that the equilibrium of V double prime, that is the ground state, is equal to the R equilibrium of V single prime. That is, the equilibrium internuclear distance of ground state and the excited state and are same value. Both are the same value. That is, one ground state, excited state lies the exact top of the ground level. Quantum mechanically, it is known that the molecule is in the center of the ground vibrational level of the electronic state. It's always like that according to quantum mechanics. So in this first case, the R equilibrium of P double prime and D prime are same. The most probable transition will be P double prime 0 to V prime 0. So the strongest spectral line will be 0, line. You can see the spectrum below, and it is the 0, line is the strongest. The next possibility is that the equilibrium internuclear distance of V double prime is greater than V prime. That you can see it's more greater. R equilibrium will be greater for the excited state. Here, the probability of transition will be V double prime 0 to, as it is in the center, the normal transition will be double prime to 0 to V single prime 2. And the spectral line have the strongest line at 2, 0. There is a third case that the R equilibrium of V double prime is much higher than V single prime. There would be a transition that it is very close to the dissociation limit. In this case, the molecule may dissociate and results in a continuum in the spectrum. There will be no spectral line, only a continuum will be obtained as the molecule gets dissociated. By Frank-Condon principle, as the molecule does not get enough time to change its internuclear distance, that is the R equilibrium appreciably, the most probable transition according to Frank-Condon principle will be the 2-0 transition. 2-0 line. The first possibility may be completely omitted by this principle. But the third possibility, which we have to consider in detail in electronic spectroscopy, that is the concept of dissociation and pre-dissociation. The dissociation, as we have already said, the excited state is considerably greater than in the ground state. Hence, the transition promotes the molecule into a point where its energy is far above the potential energy plateau of excited state. As a result, the molecule gets dissociated and we will get a continuum in the spectrum. Consider now a slightly different case of a diatomic molecule which has a potential energy curve X in the ground state and two potential energy curves in the excited state A and B, where the curve B indicates an unstable state which does not have a minimum. In this case, the molecule may also get dissociated if it is excited to a level below the plateau of A. But where at the point C, where the potential energy curves A and B cross each other, at an internuclear distance corresponding to this point C, the molecule may undergo a crossover from one state to the other without energy change and continue to dissociate. But above the point C, the molecule may have normal transitions with sufficient intensity and the spectrum would be like this. That is, there would be a region of pre-dissociation maybe, and along with strong transitions in the lower wave number side and the higher wave number side. This is the concept of pre-dissociation. These are some basic aspects of electronic spectroscopy, and we will come to the details of this electronic spectroscopy in the coming lectures. And I am concluding this lecture here. Thank you, my dear students.